Kylie, we're doing this for you. And others. Megan, we could show it to
Carly
Megan.
don't like you.
There you go, James.
Okay, so I showed you this on Thursday, just before break, and we were talking about how as you heat up a substance, you can heat a solid until it gets to its melting temperature, and then when it starts to melt, it does not any longer change temperature, it just stays at the same temperature. It stays there, it stays there, until all of the solid has melted down. Then once you have a liquid, a whole liquid, then the temperature will start to go up again. But during the phase change, the temperature's not changing. I'm going to suggest that you just take a moment and copy this graph down. You don't have to put any numbers on it. There's not a single number on the graph. But just the shape of it is significant. The x-axis is heat. As we go to the right, there's more and more heat added. And the y-axis is temperature. And you need to recognize that during the transitional sections on here, the temperature is not changing. That's where the physical state changes. As you draw too, I want you to notice something. Did anybody notice that my melting region was this long and my boiling region was this long? Do you think that was on purpose?
Yeah.
It was on purpose. It takes more energy to boil a liquid than it does to melt the same solid. If I have 1 mole of water, for instance, melting a mole of ice takes a certain amount of energy. It takes a lot of energy to melt a solid. But then to get the liquid of that same substance to boil, that takes more energy. Can you think of, imagine what the particles look like and what you're doing to the particles. Why would it take more energy to boil a substance than it would just to melt it from a solid? Yeah, I know that you're at a higher temperature here, but the flat area is farther here. It does take more heat getting a substance to boil at its boiling point than it does to melt at its melting point. What are you doing to the particles that would require more heat? Can you imagine that?
You're
You see the
separating
particles
them?
doing. What's that?
Separating them?
Exactly. That's exactly what it is. You're completely separating the particles away from each other. When you have a solid, the particles are up next to each other, and they're kind of stuck in position, but they're moving around. They're vibrating. Not really moving around, but they're moving back and forth. And then as they melt down to a liquid, they're still very close to each other, but they're able to move around one another more. But you have not really broken them so much apart. You've broken the attraction holding them stuck in their position. But when you take a liquid and you need to make it a gas, you've got to completely separate the particles from one another. That takes a lot of energy. So you'll always see the boiling flat part is going to be much longer than the melting. For any substance, water it's true for, but all substances are the same way. All right, so just a nothing. A couple of things about this. You need to understand the temperature is not changing when you have a phase change. That's why we have those flat regions. So during melting or freezing or boiling or whatever, yeah, the temperature's changing, and yes, heat is being put in or taken out. And just because the temperature's not changing doesn't mean that there's not an exchange of energy. There definitely is. Just know that all of the energy is changing the physical state, not changing the temperature. That's just during the phase change. So understand, when you see those flat regions, and now hopefully you've drawn a picture of that, in those flat regions, you can't use this equation to find how much heat is being added. And Q equals MC delta T doesn't work because there's no delta T. If the temperature's not changing, then that term is 0. It doesn't mean, though, that Q is 0. We have to use a different formula for the finding the heat of boiling or of melting. Oh, there's something melting right there. Which direction is the heat flowing with these popsicles? Heat going in or heat going out? What? Did you say out? You meant in, though, right? Or you said in, but I just heard you wrong. Yeah. It is going in, right. When a solid melts down, it's got to have energy put into it. So the popsicle is gaining energy. What's it gaining energy from? Where's the popsicle getting its energy? It's melting, so it's got to be getting energy from somewhere.
The sun.
Well, yeah, if it's out in the sun, yeah. But if it's not in this, what if it's inside?
The oxygen.
From the air around it, yeah.
Mm-hmm.
It's from air around it. The air is probably around 20 degrees Celsius. Popsicle is around 0 degrees Celsius. So the warmer air is putting energy. Remember, the warm thing is always going to continue giving heat to the cool thing until they've reached thermal equilibrium. Are they at thermal equilibrium right now?
No.
No, they're not. This popsicle is still cold. If I put my hand on it, it's going to feel cold. And when will they be in thermal equilibrium? When will the air and the popsicles be in equilibrium with each other?
When it's all melted.
When it's completely melted and the liquid, that drooly liquid, which is all over the place now, is the same temperature as the room. That's when they're at equilibrium, and no longer will energy be exchanged. Right now, yes, definitely this situation, the air is still giving energy to the popsicle, and so very slowly it melts. Why is it very slow? Because it takes a lot of energy to melt a solid. No matter what the solid is, water especially, but all solids is true. All right, so here is the equation that we use when a liquid, or I'm sorry, when a solid like this is a terrible picture too, melting ice cream melting down the cone. Do you like it when that happens?
No.
No, me neither. You got to keep on top of that. So the amount of energy, look at that, there's a Q, that means the amount of heat. And we are going to calculate that Q, just for the melting part, is going to be this delta H with a little subscript, fusion. I'll tell you what that means in a moment, times the number of moles. When you write that down, put a box around it for yourself. You'll want to refer back to that. This term right here is a constant. It's kind of like specific heat, but it refers to just the melting process for a substance. So the heat of fusion is the amount of energy that it would take to melt 1 mole of a substance. So if I can run you back just for a moment to this, that equation that you just wrote down, put a box around, that refers to the amount of heat right here. The amount of heat to go from the solid phase to the liquid phase is right there, and the amount of heat is going to be determined by how many moles you have. You multiply that by what the heat of fusion is. Normally I'll give you the heat of fusion in a problem, and we'll do a couple example problems together. Okay, you want to write this one down too, because normally we'll use water. Sometimes we'll use other substances, but almost all the time we're dealing with ice melting, if we're going to deal with melting. So the heat of fusion for water is 6.01 kilojoules per mole. Notice that this is in kilojoules. I gave my other Qs last week in joules. But it takes a lot of energy to melt a solid. So normally it's given in kilojoules. That would be 6,000 joules. So again, that means that 1 mole of water is going to take 6,000 joules of energy to melt it down. Right? I said water. 1 mole of ice. So if you have a little chunk of 18 grams of ice, it would take 6,000 joules, or also known as 6 kilojoules, to melt it down.
Bless you.
Okay with that? Now for boiling, I'm just going to give you both of the equations at once, and then we'll do a couple of example problems together. The Q of boiling is really the same thing, except it's a different constant that we're going to use. Q for boiling, the amount of heat required to boil liquid, is the heat of vaporization. It's a different number, a different constant. Still in kilojoules per mole, but it's the amount of energy required to boil a substance. And write that down, that the heat of vaporization of water is 40.7. And again, I'm going to run back to our graph. This thing, I had told you before, this line is shorter than that line. This is a much longer line. I illustrate that with this. If you have an ice cube that's at 0 degrees and it's going to start melting, if you want to melt that 1 mole of ice, water has a molar mass of 18 grams. So you've got that 18-gram chunk of ice. It's going to take 6 kilojoules to melt it. So once that 18 grams is melted down to a liquid, then you'd have to raise its temperature. You have to keep adding heat, raising its temperature all the way up to 18 degrees, to 100 degrees at 18 grams. You get it to 100 degrees. Once it's at 100 degrees, now you've got to add almost 41 kilojoules of energy to get it to boil. How much more energy does it take to boil than just to melt the solid? It takes like 6 times or 6.5 times more energy to boil the water, same amount of water, as it does to melt it. So that just should give you a sense that, yeah, boiling does, and it doesn't matter if it's for water or any substance, it always takes more energy to boil something than it does to melt the same amount of the solid. Now you don't have to. Go ahead. All right, here's a couple of example problems. So the heat of vaporization is just the amount of energy it takes to boil 1 mole of a liquid. Really is a parallel concept to heat of fusion. Okay, so if we have a big chunk of ice, 450 grams of ice, it's about a pound of ice. If it was at 0 degrees, how much energy would it take to melt the ice?
I think about 100.
No way.
Yeah.
Can't be that much.
I agree with her.
And nobody can do it that fast, Emma.
Yeah, photograph it. And it's pretty good. I just read that real quick in my head.